In this video, we have a cart moving at 1 meter per second towards a spring, and the spring is going to compress it and then push it back out to the left, and we're going to solve for the average force applied by the spring on the cart. So when I'm taking a look at this problem, it makes me think of energy and momentum. But for this problem, a couple different ideas pop up for me, and then we will use some of them, but not all of them. So if we're taking a look at the average force, I think that we may possibly use work equals force times distance and use some energy ideas, or we might use impulse equals force times time of impact for obvious reasons that both of those have force in them. So if I'm taking a look at this scenario right here, I'm going to ask myself, am I able to find work and distance? Am I able to find impulse and time? And then if so, I could do one step of algebra and then find the average force applied to that 2 kilogram mass. So out of these two options, the amount of work done by the spring compressing in and then being stretched out, and then along with the distance, that sounds a little complicated to me. I think normally the route I would think of is that the change in momentum would be fairly easy to find. And then also finding the time that the cart is in contact with the spring is actually not super hard, but it is definitely possible. So the route that I'm going to take is the delta P equals F times T, which is mv final minus mv initial, which is basically m times delta v, v final minus v initial. Now, assuming that no energy is lost through friction, heat, sound, or anything like that, if it gets compressed and then pushed back out, it should still have the same amount of kinetic energy, therefore have the same velocity. But if it's flung back in this direction, its final velocity would be -1. So we have a mass of 2 kilograms, we have a final velocity of -1, and then we have initial velocity of 1. So it's basically 2 times -2, and then the impulse comes out to -4 kilogram meters per second. So that covers our first variable that we're looking for. Now the time one is a little bit tricky. So one of the realizations that you need to come to is that as this thing is crashing into the spring and then pushing it back out, it follows a motion that is very, very similar to simple harmonic motion. It's just not rigidly attached to it the entire time. So with that being said, we have the period, which is 2 pi square root of the mass over the spring constant. Now, when it presses into the spring, we have the mass of the 2 kilograms, and we have the spring constant of 50. Now, the thing is, the T is one complete cycle. So it would be something along the lines of like if the cart were to compress the spring in all the way, come all the way back out, and then return back to that position again. That's one full cycle coming back to exactly where it started. Now, if the cart's coming in and then touching the spring and compressing it in, it's actually going to release it at this point right over here, and it's not going to go all the way out and back in. So we actually only want half of this period. So we're going to take our entire answer and divide it by 2. So if I found the regular period, it comes out to 1.26 seconds when I just plug in this numerator part over here. And then I'm going to cut that in half. And then the time of half the period is 0.63 seconds. Okay, that covers the entire time that the spring was in contact with the cart. So that covers both of the things I was looking for. So now I have 4 kilogram meters per second equals force times time. And as I said before, we only need to do one simple step of algebra, divide both sides by 0.63. And then my final average force comes out to 6.35 newtons. So if you're working out a problem like this, basically what you're going to do is use an impulse formula to find your delta P, your change in momentum, And then also you're going to need half of the period by finding your 2 pi times the square root of mass over k, and then splitting that in half for your time of impact with the spring and the cart. And then you plug that into the formula so that you can do your last little step of algebra and then find that average force. So I hope that was helpful to you. Thank you for watching and listening.